Yeah, just catching up. Welcome to the convo.
Is Jeremy here?
I'm not sure, but I like that video you shared the other day regarding the uh the transist capacitor.
Yeah.
Sorry, what about a capacitor? I'm here though. What's up with the capacitor?
Yo, so check it out. My new
Piezo,
favorite
what
go-to
up?
proof.
What up?
My new favorite go-to proof, like low level, very simple to understand one, not like a super high level science one.
Oh, you got some DJ Clue new shit? Let's hit us with it.
It's archaeoastronomy, bro.
That's dope. Yeah, archaeoastronomy. Up like Göbekli Tepe was kind of thing, right? Great pyramids. What else? What else you got?
Specifically because of the precession of the equinoxes. So
Oh, you're
the
not talking about the
equinox,
Sphinx. You're not talking about things being an equinoctial marker, are you? Like the Sphinx and
yeah,
shit.
yeah, like the slots within like various temples across the world and other ancient structures like Stonehenge, for example, they will mark the position of the sun's zenith at like on like the equinox and or like sunset on like the solstice and stuff like that. So
But
the
bro, here's the
precession of the
thing though.
equinox doctrine.
Hold
So
on, here's the precession of the equinox though. That's the stars in relation to the sun. The sun don't change. If they're lining shit up with the sun, that's not
oh 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 oh
what's
it
that?
has they both have to change. What's the cause?
The cause of what?
In the globe model, okay, so they say in the globe model, the way that they know it's happening is that they can take measurements of the stars with respect to the sun and measure their relative positions and see that the position of the stars with respect to the sun changes. Right? Okay. Right? They say this is a consequence of Earth's motion, Earth's rotation. Earth's rotation has a little wobble in it and it causes it to precess around on a 25,000 year cycle. Okay? Gaining 1 degree of rotation every 72 years, multiply that by 360, you get like 25,000 something. Okay. So basically what happens is every 72 years, the reason that the position of the celestial sphere with regard to the sun changes is because they know the earth only ever orbits the sun, is that there's like a wobble in Earth's rotation which causes its rotation rate to not be perfect. And so every 72 years it gains 1 degree. Okay? So that over 25,000 years it'll go through a full rotation with respect to like the solar system frame. So on Earth, since it's only one cause, the same singular cause as Earth's rotation, it would have to affect everybody in the sky. Okay? So that means that, I mean, you can ask ChatGPT, ask it. Be like, okay, the precession of the equinoxes, there's 1 degree gained every 72 years. So does this mean that if I have a series of mountain ranges in the horizon separated 1 degree apart, that every 72 years the position of the sun at its apex on the equinox will move over one mountain peak every 72 years? Over 720 years, it would be 10 degrees. See what it says. It will tell you yes. And it'll go through, and if you ask it to explain the full great cycle, it'll say like the Earth goes through like a 360 degree orientation change every 25,000 years. If this is true, then at noon on the equinox, every 72 years, the position of the sun would be shifted 1 degree. 720 years would be 10 degrees. 1440 years would be 20 degrees, etc.
For the
There
sun
are,
though?
yes, the position relative to an observer on the ground, where you see the sun in the sky at noon on the equinox would change. It's called the precession of the equinoxes. This is the globe model requirement.
Hold on, let me just think this through. Because I didn't think that was supposed to happen. I thought it was just the star. I thought the procession was just the stars in relation to where the sun rises on an equinox. The backdrop of the stars change, not the sun. You're saying that their model says that it's supposed to shift though.
Yes, the position of the sun in the sky on the equinox at solar noon will be a different spot.
Why? Hold on,
So, like,
hold on, Piezo.
That's
okay,
not correct.
I was gonna say we got Danny in the house. Go
The
ahead.
the precession of the equinox will cause the position of the sun to change with respect to the stars.
okay.
Relationship to the where it is in our sky, how many degrees up it is, and so forth. That's not going to change. It's just the stars are going to change in the background of the sun.
So, if you're not making any calendar corrections, okay, if you're not accounting for this change on the calendar, then that would mean that the position, because the way you would compute this is from a geocentric frame, from the Earth frame. That's the way you would compute it just to make it easy. Okay. So if you don't make a calendar correction and the sun comes around to the same position in the sky on noon, how would the position of the stars have changed?
Because the sun's position with the star has changed. The stars haven't changed. The sun's position. The precession would cause the stars we see at night, for instance, to change. Right now, Orion for us is a wintertime constellation, but in 12,000 years or so, 13,000 years, it will be a summertime constellation.
Okay. So my point is then this is caused by an Earth rotation effect, right?
Yes, the what's going on is the Earth's rotation axis is moving with respect to the stars. Right now, the pole star, the Polaris, is very close to that point, but it wasn't always that case. 4 or 5 thousand years ago, the star Thuban was much closer, and about 12,000 years, Vega will be closer. All it's doing is changing the background of stars we see.
It means that the Earth, instead of being on the north side of the sun, would be on the south side of the sun in summer, right?
Well, yeah, the not in summer. Our seasons are based upon the tropical year, and so that's going to cause the seasons to be fixed. The June solstice will always go to summer in the northern hemisphere, except the stars we see at night will not be the same.
The only way the stars you see at night could be different would be if the sun is on it, or the Earth is on the different side of the sun, because the stars don't change.
Yes, that's correct. What it means is right now
Okay.
when we're on one side of the sun, it's summer in the northern hemisphere and winter in the southern hemisphere. But in 13,000 years, summer for the northern hemisphere and will be on the other side of the sun.
Right. So if you were on the other side of the sun, would it still be summer?
In 13,000 years, yes, it will be because our calendar keeps the tropical year, which fixes the year's length to the sidereal year.
Okay. So you're saying it would be summer on the other side. So
Yeah.
if it would be summer on the other side, would we be cold in the summer and hot in the winter?
No, the temperatures would be similar to what they are today.
No, they wouldn't, because when you go to the other side, that's what causes the change of the seasons.
No, it's the tilt of the Earth's axis that causes the seasons.
Okay, but
In,
if the tilt is, bro, I wish I was on my computer and paint. I'm driving right now, so I can't draw
in,
this.
in
Come
13,000
back when you.
years, will in summer will be on the other side of the sun. The northern hemisphere will be tilted toward the sun, so it'd still be summer.
Right now, during summer, let's say the Earth, the axis of the Earth, we're in like a solar system frame. We're looking down on the Earth and the sun. When the Earth's axis is tilting from like bottom left to top right, okay? When the Earth is on the left side of the sun, the top right is towards the sun, which is the northern hemisphere. So when Earth is on the left side of the sun, it is summer in the northern hemisphere. When it gets to the other side, the top right is tilted away, so it's winter in the northern hemisphere, right?
No, when you get right now, yes.
Okay. So if you shift this 12,000 years from now, in order to see the opposite side of the sky during the day, the Earth would have to be on the right side of the sun during the summer months. But if it was doing that, then the northern hemisphere would be tilted away, so we would be tilted away during the summer, making it cold.
But the tilt would be the other direction, back towards the left.
Okay, so the pole axis of Earth on the right side is now tilted towards the sun.
Yes. In years, it will be tilted toward the sun.
How does he not see this?
Okay.
So tilt towards, tilt away, both same temperature.
Right, so if we just keep the Earth fixed on the right side and we just shift it by 1 year on the summer solstice, all we would see changing would be the axis of Earth would be rotating around year after year after year after year until it made a 360-degree rotation in 25,000 years, right?
Right back to where we are now.
Okay. So when it is 12,500, whatever years apart, the pole axis angle tilt has shifted 180 degrees from being away from the sun to being towards the sun, right?
Yes, and so it will be on opposite sides of the sun, and the stars we see at night would be totally different.
Okay, so now when we go to March, for example, where where it's at the equinox, where it's at where it's like, let's say above the sun. We'll say it's above the sun, okay? North of the sun in this like fixed grid.
The equinox will be above the
Yeah,
sun?
it's above, on the equinox where it's a fixed grid. Before the axis was tilting to the right, now the axis is tilting to the left, right? That is a 180-degree shift from the side of the Earth facing the sun on the day of the equinox. So your midnight and your noon have shifted 180 degrees.
Yep.
This is why the equinox is precessed. It's called a precession of the equinoxes. So the position of the sun during the day, 72 years would shift 1 degree on the equinoxes. On summer and winter is where it balances out, because those are always based on longest and shortest day of the year. But on the equinoxes, because it's in the midpoint, the position of the Earth on the equinox is still on the same north or south side of the sun, but the pole axis has changed, making where the sun is at noon on the Earth's surface a different spot. Because if we do that whole swivel change, if we, instead of keeping the Earth on the right side, if we keep it on the top side and we do the swivel change, as that swivel changes, solar noon on Earth reaches a different surface point on Earth every different point throughout that 25,000 years.
No, it's different. The different spot in the sky with respect to the stars. From the surface of the Earth, if you're measuring altitude and azimuth of the sun, it'll be the same.
Tilted towards the sun, tilted away from the sun, same temperature, right?
Yeah,
I'm
summer
talking about the
temperatures.
equinox. So the equinox, where Earth is like up above the sun, it's like north of the sun from the top-down view in the solar system frame. We start with it up there, and the axis is running from bottom left to top right. And so we start looking down from the above it, northern hemisphere view, and we see it pointing down, and that axis starts turning. So at the day of the equinox, where the sunlight is pointing straight up towards a point on the ground, the solar noon, okay, every year, we'll say every 72 years, that axis precesses 1 degree around, So it's 1 degree of longitude that's changed of where solar noon is. Solar noon changes by 1 degree of longitude every 72 years on the day of the equinox.
The position of the sun in the sky will be different with respect to the stars. With respect to the stars, I think that's what you're confusing here. You're thinking somehow on the say the March equinox, the sun in 13,000 years will be in a different part of the sky at local noon than it is, and it won't. It'll be in same altitude and azimuth it has now. It's just the background stars will be different. The March equinox right now is between the constellations Aquarius and Pisces. 2,000 years ago, it was between the constellations Aries and Pisces. 2,000 years between Taurus and Aries. We use a little symbol for the vernal equinox called the first point in Aries. In fact, sometimes it's called the first point in Aries, even though the vernal equinox has not been in Aries in 2,000 years. All that's shifting is the position of the sun on any given date of the year with respect to the stars. It does not affect where you'll see the sun in the sky. We'll still have it local noon. It'll have an azimuth of 180 degrees and an altitude depending on
with respect to the Earth.
what the latitude is.
So you're saying the wobble's only happening because this happens because of the wobble, right? Or is this because the stars are
The Earth's
4 minutes?
rotation axis is going around an axis that's 23.5 degrees from the orientation of the axis, so it spins around. If you look at a gyroscope or a top that precesses, it's going on.
I was on a phone call. I was on a phone call that whole time. I missed everything.
The 23.5 is relative to the Earth, though.
Well, it's the tilt of the Earth's axis from our orbital axis.
If you're tilted,
the plane of the ecliptic.
Off the plane of the ecliptic, yeah.
23.5 toward the Earth and 23.5 away from the Earth, can you have the same temperature?
Yeah, similar.
The Earth can be tilted 23.5 degrees towards the sun and 23.5 degrees away from the sun and be the same temperature.
You mean the different hemispheres you're talking about?
Danny just said no.
Well, I thought you were saying that we weren't having seasons at all. When you're tilted, and when you're tilted away, and you tilt away, you have winter. So when we have summer and the northern hemisphere, they're having winter, and 6 months later it's reversed. But the temperatures of summer from one hemisphere to the other is roughly that of the other hemisphere.
Wouldn't the South be vastly different? Real quick, just on that note, wouldn't the South be vastly different because it's reflecting more light because it's mostly oceans or something? Like when it get hotter in one and warmer in the other, or colder in the other?
That's where it gets very tricky. As it turns out, we're at perihelion in early January, about 2 weeks after the December solstice. That means we're closest to the sun by about 3% or 3 million miles in January than we are in July. And so oftentimes people weren't taught very well in school. They were told that it's the changing distance from the sun, tilting toward away from the sun, that causes the seasons. And that's obviously not true, because if it were, everybody would experience summer, January, winter, and July. And that's true in the southern hemisphere, but definitely not in the northern hemisphere.
It's opposite, because we get closer, but it gets colder. We get closer to the fire basically, and it's getting colder.
Well, no, we're closest to the sun in January.
That's what he's saying.
Yes, and it's my winter time.
Right, and you might think then, well, the seasons in the southern hemisphere might be more extreme because the southern hemisphere is farther from the sun in their summer. Closer to the sun in their summer and farther away in their winter. But in reality, the southern hemisphere is about 90% water, and what the water does is it acts as a thermal buffer.
I think the terminology I use should be corrected. I said solar noon, but I should have said 12 noon. The thing is 12 noon is supposed to be solar noon, right?
Yes.
But
yeah.
Let's talk
time is noon.
Yeah. Let's talk calendar time, though. If we keep calendar time,
calendar time is date of the year. Solar time or local time is time of day.
Right. But okay, whatever terminology. Let's just say clock time. I've got a clock that is exactly dead on accurate for 24 hours in a cycle. Okay, or 2/12s or whatever, however you want your clock to work. And 24 hours is 24 hours. Then that means Earth resetting back up to the top every 72 years, 24 hours is 24 hours. The position of the sun at zenith on the equinox would no longer be at exactly 12 o'clock. Every 72 years, it would precess 4 minutes. Yeah, 4 minutes. No.
But the problem is you're talking about clock time, if you will, be the time of day. That only works from one day to the next, and the calendar is a longer term. Our calendar is based upon the tropical year, which is defined with respect to the equinox. So every year we will come back to the same position with respect to the equinox. Forget the 72 years, we'll still be back there because that's the year we're based upon. You're thinking of the sidereal year, and the difference between the sidereal year and the tropical year amounts to a difference of 1 degree every 72 years. We don't keep the sidereal year, we keep the tropical year because we want to keep the seasons in sync. We don't want to keep the stars in sync necessarily with our calendars.
Yeah, but we don't have calendar corrections. All we have is a leap year. That's it. And that adds up to 18 days every 72 years.
$18 days every 72 years? No.
Yeah, because we gain one day every week.
But that's what's the point of that? I don't understand what you're saying.
I'm saying that there's not a correction built into our calendar to adjust the hour of the day.
You're right. The hour of the day goes from noon to noon, and it the calendar is based upon the tropical year. I think they're confusing the two issues of the daily rotation and the annual motion.
Yeah. So does it take 24 hours or 23 hours 56 minutes for Earth with respect to the sun to rotate 360 degrees?
24 hours. It takes 23 hours and 56 minutes with respect to the stars.
Okay. So that means starting up at that north of the sun part, day of the equinox, I can just do a whole bunch of 24 hours cycles and get back to where I was.
Yeah, basically.
Okay. But during that time, the axis of Earth is changing. So if I keep my 24-hour time cycle exactly until I reset back to that same spot using only 24-hour increments, but the axis has changed, that would mean that the longitudinal degree that is lined up with the sun has now changed because the axis has changed and the whole Earth has processed around.
But you're still turning about those miles per hour. You're still
It cannot be simultaneously 24 hours and have the whole entire Earth as a whole shifting around without doing a correction for the difference between those two things.
You're still turning at 1,000 miles per hour, no matter what.
What?
Your rotation on your axis is still the same.
Yeah, but the whole axis has shifted.
No, the axis in terms of angle, that's fine. You really don't. That doesn't matter to you. You're still turning on your axis. You're still turning at 1,000 miles per hour. That doesn't change.
Okay. Is the Earth itself the ground fixed to the axis? Yes. That means if the axis shifts, the ground shifts.
With respect to the stars.
Yeah, exactly. and where it's pointing to the sun. That's all. Your rotation speed is what's determining your day.
Okay. How can the axis shift with respect to the stars and not the sun if all we're doing is resetting back to the same point in 24-hour increments? That would suggest that the whole solar system is rotating with respect to the stars. Because if we're in our fixed solar system grid and the sun is just moving horizontally, and we can treat it as not moving at all, basically, because the stars are infinitely far away for our purposes of calculations, then that means using only 24-hour cycles where we can reset the sun back to the same equinox spot as it was a year ago, using only 24-hour cycles, the axis of Earth would be precessing around with respect to the entire spatial background.
The equinox in that 1 year, I should say, it's going to move 1/72nd of a degree along the ecliptic, and so when you line up with the sun, say at this March equinox, and you wait and come back a year later, the sun will not be in the same spot with respect to the stars. But we reckon our time of day with respect to where the sun is. So noon will always be noon, even though the stars appear to have shifted a little bit.
From a geocentric position, we would just say that the stars move, that the celestial background moves.
Yes, that's correct.
Yeah, but in geocentric, your ground is a globe. So you know. In geocentric, your ground is a globe. You're on a globe. That's what geocentrism is. So flat Earth is different from geocentrism.
So the two arguments are not the same. They're talking about different topics.
No, I just want people. I'm just pointing that out. A lot of people are confused with geocentrism and kind of flat Earth versus heliocentric. Those are three separate things.
Have to be a sphere. You could have a spherical geocentric model if you wanted to talk about that, but just the word geocentric.
Those are three separate things.
Have to be a sphere. You could have a spherical geocentric model if you wanted to talk about that, but just the word geocentrism doesn't necessarily indicate a sphere.
Oh, absolutely it does. That is the whole premise of geocentrism. It's spherical.
All right, so the word is geocentrism. It's not geocentricism. So first you should get the word right. It's geocentrism.
I have an accent. I apologize, Brad. Don't worry about it.
The classical geocentric model was a spherical Earth, but the flat Earth would also necessarily be geocentric. It would just be a very different sort of geocentric model.
Yeah, you can't have geocentric at all on flat Earth.
No, you can't. I mean, the flat Earth posits that the Earth is not moving at all. I think what you're thinking of is the classical geocentric model from antiquity, and it was based upon a spherical Earth. So there are two very different geocentric models, but flat Earth is geocentric.
No, flat Earth cannot be geocentric.
Well, then what's the flat Earth moving around?
The flat Earth is a stationary.
And the geocentric Earth is stationary too. The spherical geocentric Earth is stationary.
Yeah, it would be more like a the way geocentrism would be described with a planar Earth would essentially be more like a if you have like a hamburger and you have the bun on the top, the bun on the bottom, the meat in the middle. It's like the meat in the middle would be the plane in the center. You have the sky above, you have the underworld below. So in that case, geocentric would really be like Earth centered, be like the meat in the middle of a hamburger kind of thing, where it's like centric, it's geocentric, Earth centered in relation to what's above and what's below.
Right. Geocentric is things are orbiting, not circling. There's orbiting. On flat Earth, things are circling above the ground. Those are not orbits.
But the Earth is still not moving in that model, so it technically is a geocentric Earth. But I say again, it's not the same as say the Ptolemaic or the Aristotelian geocentric Earth. The Aristotelian and Ptolemaic models were a spherical Earth that remained motionless, and everything went around it. The flat Earth also remains motionless, but things are moving above it. It's a geocentric model.
Yeah, but the ground is on the bottom, so things are not going around it.
Sure, but again, geocentric literally means geocentric. Literally means Earth-centered. I guess it doesn't mean geostationary. Maybe you're making the point of geostationary, which is a different thing.
Right. I mean, Earth bottom. Right. There's a dome over top.
Yeah.
So on top.
I think that I understand what you're saying now. You're
sorry about that. So check it out. So I had to go in the gas station. That's why I had to go for a second. I'm back. Back to the illustration. I thought of a better way to illustrate it. The Earth, with respect to the sun and the stars and everything, is still north of the sun. It's still in the same spot, reset back to the equinox day, which the equinox day is still the same spot. The position of the Earth in the whole system doesn't change. It's just the axis of Earth, right? Because basically, on the day of the equinox, because of the axis of Earth, the stars at midnight will be lined up to a different point on Earth's surface than they were before, because the side of Earth that's facing away from the sun, like as far as, will be a different point on the ground than it was before. So it's about the relationship of the stars in the sky to where they are on the ground. The Earth, because its axis is no longer pointing to all the way to the right, but is pointing, in some other direction, when it gets back to that same spot where it was perfectly north of the sun, then nighttime, the same star that's directly north of the sun in this grid will be hitting a different point on the ground at nighttime, at midnight, than it was X many years ago, because the entirety of Earth's axis will have shifted, which in like manner means that the part facing directly south towards the sun will be hitting a different spot on the ground than it was so many years ago. Now, you can define local noon as being when the sun is at apex, right? But I said 12 o'clock. We established that 12 o'clock is when Earth gets back to that same spot in the grid.
With respect to the sun.
With respect to the sun and everything. The whole entire, it's the space frame, bro. It's the space frame. I'm talking about the sun is stationary. The background stars are stationary. The only thing that's moving is the Earth. It resets back to the same point straight north of the sun, but now its axis is shifted, meaning that the point of the ground facing the stars north of the sun has shifted. Also, the point of the ground facing the sun south of this spot has shifted.
What you see in the sky will be the same. Suppose you went out on the March equinox and you measured the altitude and azimuth of the sun throughout the day, from sunrise to noon to sunset. And then you had a time machine and you went 13,000 years into the future, and you repeated this again on the vernal equinox. You're going to measure the same altitude and azimuth of the sun the second time as you did the first time. The only difference being is the stars would be that were up would be totally different in the second from the first.
Bro, if we just use the space grid, which has our entire solar system in it, and the position of the sun with respect to those fixed background stars is not changing. It's like a rigid system. The only thing moving in our view is the Earth. And my point is the Earth, if we reset the Earth to the same exact point it was with respect to the sun, which is what a year is, the only thing that changes is when it gets there, its axis will have rotated around.
You're talking about after half a precession cycle?
Any year, year to year, it's just a small amount. Every 72 years, it'll be 1 degree.
Yeah.
Okay, so I'm defining a year, which is the definition for a calendar year, as the sun resetting back to its same exact spot it was with respect to the sun a year ago.
Oh, well, the sun is the same spot with respect to what? There are two different years at play here. One is the sidereal year. If you note the position of the sun with respect to the stars, and you wait 1 year, then you will be one sidereal year. Then you'll be back to where the sun was with respect to the stars. If you talk about the tropical year, then it's with respect to the equinoxes. And I think the difference between the 2 years, as I recall, I'm working from memory, is about 20 minutes. So from 1 year to the next, there's a 20-minute difference between the sidereal and the tropical year. But our calendar is based on the tropical year, and that keeps the seasons fixed with respect to our months. So March will always be the beginning of spring in the northern hemisphere. June will be the beginning of summer, and so forth. If we kept the sidereal year, but all a prominent constellation in December, but summer would eventually occur in December rather than June, and that's we don't like that. We'd rather keep the calendar fixed with the seasons, not to the stars.
Okay.
I think you're trying to drag the stars along with the sun through the precession cycle, and it can't be done.
Yeah, I said I'm using the solar system frame, where we are rigid, fixed within the solar system. We've got a fixed background and a fixed sun. Okay. 1 year is defined as when the Earth moves. I'm using it like spring equinox, where the Earth is like to the north of the sun. 1 year is being defined in this frame as when the Earth does one full circuit and comes right back around to the same exact spot it started.
With respect to
That's with respect to both the sun and the stars, bro.
You're not allowing for precession to take place. You're defining it away.
No, I'm not changing precession. I don't care if the Earth does like 720,000 like rotations and does because it's someone like flicked the axis with their finger and it started like wobbling. Just the whole Earth as a whole has come back to the same spot in this solar system grid.
With respect to what? I ask again.
Dude, it's with respect to everything.
Well, here's the point. Suppose that you observe the sun at the March equinox, and there happened to be a star right there. So you've got all three lined up. The sun, the star, and the March equinox are all happening in the same place, the same time. If you wait for a year and you come back, the stars are not lined with the sun, and the equinox will not line up with the sun at exactly the same time. The time difference will be about 20 minutes. You can't have both of them fixed. You're trying to fix both of them, but you can't. You either measure the sun's motion along the ecliptic over a year's time with respect to the stars or with respect to the equinoxes, but you can't do both. Now, the fact that they're both close to one another means you can get away with it in the short term, but if you do it year in and year out over the centuries, you will end up with you can't do it anymore. They just simply won't match up. All three of them won't.
Hold on 1 second. Okay. I am forget about we're going to start from first principles here. We're going to forget about what time you think it is, what hours in a day are, what sidereal years are, or what a solar year is, or any of that. All I'm talking about, we have a solar system. We are centered over the sun. And let's say that, I'm just going to call it star X. Let's say that star X from a top-down view looking at the sun is straight north of the sun. Okay. There's star X. Okay. Now the entire celestial sphere is also filled in all the way around 360 degrees, but star X is directly north of the sun. Okay. It doesn't matter how we reckon time in this frame, in the solar frame, star X is always to the north, period. Now, let's define the equinox as when Earth is in a straight line between the sun and star X to the north of the sun. That is the day of the equinox. Okay. 1 year is defined as when the Earth goes a full circuit around and comes right back in line in between the sun and star X to the north of the sun. All right. That is 1 year. Now, when we use
one sidereal year.
So this is one sidereal year.
Yes.
Okay. So when the Earth comes back around 72 times, its axis will have precessed around 1 degree. Right?
And so that will be 72 sidereal years, but it will not be 72 tropical years.
Is it or is it not possible by using increments of 24 hours for the Earth to come back around to this same spot in a year?
The problem is the 24 hours a day is tied to what your calendar year is. And the calendar year is the tropical year.
Can you answer my question? I don't care what the calendar says. I already said that. We're starting from first principles. Don't bring in something that doesn't exist yet. Is it possible, using 24-hour increments only, to reset the sun or reset the Earth back to that same spot in a year?
If precession does not take place, then yeah, but it does take place.
But the Earth is on the ecliptic, right?
The length of the year is going to be different that you're talking about. You're not realizing this, but when we keep the tropical year, it defines the year to be 365.24 something. And the sidereal year is close to that, but it's not an exact match. They're going to be mismatched after a while. And so it all depends.
365.24.
Roughly, approximately, but the thing is, when you start getting out to that third and fourth decimal places, now there's a difference. So consequently, if you're keeping a tropical year, your leap year rule is not going to be the same as when you keep a tropical year. And so eventually, you think you're just going to keep coming around and coming to the same spot every time. You won't, because your leap year rule often and when to add an extra day, and it's going to be different whether you're keeping the sidereal year or the tropical year.
So once again, your answer is no. It's not possible using only 24-hour increments for the Earth to reset back to that same point in a year.
Correct. Year in and year out. Year in and year out. It can't be synced.
So if we presume now in this same system that we're in a geocentric coordinate and the entire celestial sphere rotates around to that same spot in 1 year, that's the way that we're defining a year, right? Then if we do the same thing using only 24-hour increments, right, by the time 1 year comes around, only 24-hour increments, the sky will be in a different spot ever so slightly, right?
Well, the celestial sphere is going to spin 366 times in a year, not once. It's the sun that moves once through the celestial sphere in a course of a year.
Okay. Once again, that's not what I said. I said this point that is to the north. Well, I didn't say the north part, but this is what I meant. The point that's to the north of you in 1 year, because we're defining a year as when it comes back to the same point. The point that is to the north of you in 1 year will be the same spot. So if we go into a geocentric system, it still has to be the same spot. If we use only 24-hour increments, you're saying we wouldn't be able to reach it. So in order for it to come back to the same spot, the sun would be in a different spot once it reached there.
Well, again, you've got a hidden assumption here. You're wanting the sun to come back to the same spot after 1 year. And I keep asking you with respect to what? You can make it come back with respect to the stars, or you can make it come back with respect to the equinox, but you can't do both because they're not staying fixed. Either the stars are moving or the equinox is moving. One of the two it's a matter of observation that's going on.
The beauty in this is that what I was doing is I was referencing the solar system frame, and what you're doing implicit to bring in time is you're using two different metrics for time, and both of them are referencing the ground of Earth. Like you're referencing a geocentric system, actually. Like that's kind of the point of this exercise, is to show you that in order to bring up two different metrics for time, you have to reference a geocentric system.
Well, our time basically is geocentric. The way we measure, the way we express it is essentially geocentric. It doesn't mean that the Earth is not moving. It just simply means since we're sitting on the Earth, it's our reference frame for measuring or delimiting time, measuring the passage of time.
That's right.
Okay,
you're turning on your axis.
Right. So if, for example, we were to have, I don't know, structures, I'll call them structures, where the equinox is aligned with that structure such that, let's say, for example, Orion's belt. Let's say that Orion's belt is lined up with that structure at midnight, and the sun is lined up with that structure at noon. Okay, on the equinox. As the years go by, let's say 720 years from now, either the sun at noon would no longer be lined up with that, it'd be 10 degrees shifted, or Orion's belt at midnight would be 10 degrees shifted.
Orion's belt at midnight would be 10 degrees shifted.
Okay. So if that's the case, right, we should be able to go to ancient buildings who, have shafts lined up with certain stars, and they shouldn't be lined up with those stars anymore, right?
Well, that's what's claimed for one of the passages in the Great Period of Cheops. They say that it was aligned with Thuban as a pole star when the pyramid was constructed.
Who says it was lined up with Thuban? That's what scientists say by going back, but it's lined up with Polaris right now. But
actually, it's not lined up with Polaris. The angle, it doesn't. The Polaris is not exactly the North Celestial Pole, and certainly a few thousand years ago it was pretty far away from the pole. Polaris was actually started to be called the pole star about 500 years ago.
So if I look at the history of archaeoastronomy, you think that you could provide evidence of that?
Well, not of that per se, but we do have records that indicate positions of these things. One can look at the Ptolemy's star catalog from 19 centuries ago, and we see that there's a systematic change in position of the stars over that length of time. In fact, from 1 year to the next, there are slight changes. In my work, I have to frequently precise coordinates. Otherwise, I point the telescope in the wrong part of the sky.
1900 years. That should be about 26 or 27 degrees, right?
Yeah, something like that. And what's changing is the ecliptic longitude of stars is changing. The ecliptic latitude is not. I've actually gone through some of the stars in Ptolemy's list in this itself, but it's pretty well known. This has been the first person to notice precession was Hipparchus about 200 years, 300 years before Ptolemy, because he did a star catalog, measured ecliptic latitudes and longitudes, and noticed a systematic shift from a previous star catalog done a few centuries before.
So if I transform to a geocentric system and I say a day is always 24 hours, right? A day is always 24 hours. How can I ever get to equinoxes 3 years from now? Because the leap year is the 4th year, right?
Most years, yeah.
Okay. So shouldn't that mean that, like, if I gain an extra day every 4 years to keep, the alignment of Earth around the sun with respect to the solar system grid the same, then shouldn't the sun at noon on the equinox not be at apex those other 3 years?
No, again, it's with respect to the stars that we're worried about, and again, it's the leap days have nothing to do with what we're talking about. The leap days have to do with the fact that there's not an integral multiple number of days in a year. There's roughly 365 and a quarter. That's why we add a leap day roughly every 4th year to
So
keep it in sync.
what's that quarter day for? What do
you mean, what's it for? I mean, it's
well,
the year's length, whatever year you want to pick, is roughly 365 and a quarter days. So we don't like to keep quarter days on our calendar. So about every 4th year, we add an extra to bring it back up. 4 times a quarter is equal to 1. So it gets it back in sync again.
Okay, so when you say a year is 365 and a quarter days, roughly, it's like it's not 0.25, it's 0.24, blah, 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 whatever. But that quarter day, is that defining a year as what I defined it before for in the fixed solar system grid for the Earth to return to the same spot?
Well, again, there are several years you can pick. Sidereal or tropical are the two you were talking about, and the difference is so small that they're both very from one year to the next. There's not much difference. So yeah, it's about 365 and a quarter.
Okay, but if we're talking, okay, here's the thing. That let's just say 365.00 versus 365.2 something, 24, 25, whatever it is. 365 days of exactly 24 hours, that would cause it to still be daytime. If I add a quarter day, now I've just gained 6 hours. 6 hours. Now, if I'm talking about a year as being in that fixed solar system grid we were defining before, are we saying that it takes 365.25 24-hour cycles to get the Earth back to the same spot? Is that what we're saying?
That's
Okay.
what we're saying.
So
because
then,
if you didn't do that, then the June solstice roughly occurs on June 22nd. If you didn't add any leap days, kept a 365-day year, then every 4 years the summer solstice would occur a day earlier. Over 100 years, that would be 25 days almost. So it would be occurring in late May rather than in late June. That's why we have to add a quarter day in order to keep the sync.
but the problem is adding that quarter day, right? If we're only using 24-hour periods, then that means daylight should either shift 6 hours or the sky should shift 6 hours. Because if the Earth is in the same exact spot, lining up a straight line from the sun to the Earth to that star X that's directly to the north, then either
and that quarter a day results in a quarter degree difference. If you went three,
No,
if
it
you
would be
noted,
6. It would a day. No, wait. No. A day is 24 hours. We're defining a day as 24 hours. Remember? So
yeah.
24 hours divided by 4 is 6 hours.
Mhm.
That's that. That means that daylight would be shifted 6 hours.
No,
Or
the sun moves along the ecliptic about 1 degree per day. So
I'm not talking about the geocentric frame, bro. I'm talking about the solar system grid frame.
you're talking about the heliocentric model.
I'm talking about the solar system grid that I defined that
Yeah,
the
okay,
whole time I've been talking about that grid.
what after 365 days, the sun would require another 6 hours to get to the exact position, but you're confusing
You're saying the sun.
rotation.
Stop talking in dude. The reason you're confusing it is you stay in the geocentric frame. Come to the solar system grid
But you were
and
talking
speak
about,
in those terms.
but you were arguing about daylight being changed, and daylight depends upon the sun. So I can't avoid talking about the sun
Uh,
in that
uh,
context.
you can talk about daylight while still staying in the solar system grid.
Okay, but the thing is that daylight is going to shift by a quarter of a degree over those 6 hours.
6 hours is not a quarter of a degree, bro. 6 hours is 1/4 of an Earth rotation.
And the 6 hours is 1/4 of a degree of revolution throughout the year. You're confusing daily and annual motion.
But we always know that daylight resets to the same point every 24 hours.
No, it doesn't.
Okay, so now we're talking local time. So in the solar system grid, the Earth at local time, 365 days later, it'll still be 12 o'clock because we're keeping 24-hour sync. But at 12 o'clock, 365 days later, we would be 6 hours behind because it's not a full year yet, right?
The sun would not be back to the position it was 365 days later. Respect to the
Okay.
stars or with
The
respect to
Earth
the
would not
ecliptic otherwise.
be back to the position it was 365 days later. I'm in the solar system grid. So at that point, it would take 6 more hours for the Earth to get there. So if I
No,
just go back 6 hours and I don't take that 6 hours yet, right? I'm not going to add it. Let's pretend I don't add it. I'm just 365 24-hour periods exactly. I'm now 6 hours off. Okay. In that 6 hours, the Earth travels a really small amount of time, but in that 6 hours, it definitely rotates 90 degrees.
okay, let me try a different direction on this. You're saying that you want to talk about going through one rotation at a time. The sun, and you can pick whatever year you want, sidereal or tropical. Again, over 1 year doesn't make a lot of difference. So the sun, you start off at one point and it's noon, and the sun is at one particular point with respect to the year. But you go 365 24-hour periods, and when you get back, uh, you will find that the sun will be at noon again. However, the sun will not be in the same position with respect to the stars or respect to the one. If you started off the first year at noon, then that return to where it was the year before will occur at 6 p.m., not at noon for you.
So that return would occur at 6 p.m. But with what? With respect to what?
Well, when the sun gets back to where it was with respect to the stars or the equinoxes, whatever you want to pick, you're picking this place north of the sun in fixed space. I'm telling you, after 365 rotations, you won't be back to the sun in that same position. You have to wait another 6 hours for that to happen, but it will get there. But it won't be noon for you. It'll be noon for somebody else, but not for you.
Okay, so that is okay. So that's my point. Now let's go back to the solar system grid. Okay. So where the sun or where the Earth is in this circuit has not quite got back to that straight line between the sun and the stars. It's not quite there yet. Okay. It's 6 hours left until it gets there. But on Earth, the sun is still at apex at noon because we only did 24-hour periods.
Yep.
Okay. So now it's going to take 6 more hours for that star to be directly between the Earth for that star to be directly on the other side of Earth, for the Earth to be between the sun and the star.
Back to
Before I
what
go that
position
6
you
hours,
started the year before.
yeah. So before I go that 6 hours, we know that in 6 hours the Earth rotates 90 degrees. If I go to look at that star 6 hours apart from, say 365 versus 365.25, that star should be shifted to a completely different part of the sky, because it's 365.25 where it'll be straight to the north. But if 3 or 6 hours before that, it's going to be like 89.9 or something degrees different.
89, no, be 0.25 degrees different position from what it was the year before.
So so in 6 hours, it would be 89.75 degrees different.
Something like that, yeah.
Okay. But we don't see the stars on the equinox shift by 89 degrees year after year, and then after 4 years, it gets corrected. That's not what we see.
No, you're not looking at at noon. The stars that are above the horizon are going to be very different from the stars that will be above the horizon at 6 p.m.
Or we can say midnight. Midnight works too.
Okay, that's fine. Let's start with that. If you started at midnight at the time the occurs at midnight for you, and you look at the stars that are up there, and you wait 365 days to come back, the stars will not quite be back to the position they were before. They're gonna take they're gonna have to move another quarter of degree with respect to the reference frame you're talking about, but that won't occur until 6 hours later. So it's going to happen at 6 a.m., not at midnight for you.
But say the stars don't move a quarter of a degree per 6 hours. They move 90 degrees per 6 hours.
Yeah, but the reference frame, I'm talking about the reference frame you were wanting to establish.
Well, the reference frame would be local 12. The reference frame would be 12 midnight.
You're talking about the sun and the stars being in this particular part of this reference frame you keep referring to, and that's the reference frame we're talking about. You're confusing several issues.
No. The Earth 365 cycles later is not quite back to the same part, but because we're only using 24-hour cycles, midnight is still midnight, so that 12 a.m. is still 12 a.m. So you're saying that 6 hours later, the 6 hours later, that star would be aligned back with the same place it was. But
yes, and that's because the equinox is not going to happen after 365 days. It's going to happen after 365 and a quarter days. So if you saw the equinox occurred for you at midnight, then next year it would occur at roughly 6 a.m. The next year roughly noon, and next year roughly 6 p.m., and the next year roughly midnight again.
Okay, so you're saying that that would mean that if it occurs 6 hours later, then the star that's at my zenith at midnight should be 6 hours different.
Well, it's you're confusing the transit time of that and where it actually is. I'm sorry, I need to go to another appointment. Maybe we can take this up again another time.
Or 89.75 if I grant you that quarter of a degree, but
I've got to go. Thanks. Bye-bye.
Thank you, Danny. Thank you.
All right.
And thank you, Jesus Christ as Lord. That was a great convo to listen to, you guys.
I gotta go too. I gotta get a haircut, boys.
Enjoy. Join us again soon.